Hello, math fans. Here we're going to talk about curvature for 2D curves. Surprisingly, I think when I was a student, I thought, didn't we already study this? Isn't that what concavity is? No, it's something a little different. We wait until we get to 3D curves typically to discuss it because most of the discussion involves vectors. But once we have them, we can go back to 2D and we can use that to study curvature for 2D curves. Okay, so briefly, this formula only makes sense for 3D curves because of the cross product, but there's a workaround. And the workaround is just to pretend it's drawn on the ground. So I wanted to mention something about this. My goal in this video is to talk about how we make a 3D formula work in 2D, and then I'll do these two examples. I probably will follow up with a video on a whole bunch more examples, but that won't be essential to my course. There's just too many interesting examples, and I don't want to put all those in here. So we're going to draw whatever the function is on the ground, and let's call that function y equals f of x. The moment you draw it on the ground, you can give a 3D formula for it, and it typically would look like this. You say, well, I'm just going to have x be t, and y be f of t, and z be 0. And there you go. That's the same curve. Now, honestly, what most people do is they don't even make this a t. They're like, why do I have to use a t? I could just make my parameter x, x, x. And then it fits perfectly. But rather than do that for each one, we could just calculate the formula once and then use it for the rest of the time. Let's do that. So r prime of x is going to be 1, f prime of x, 0, r double prime of x. This is actually really fast. I just wanted to show the derivation. There you get the second derivative. We need to take the cross product of those things. So we'll do a little I, J, K business here. Let's do that now. My students know I have a certain routine for doing these until we get really good at it. And you should also always check your work. So this is going to be 0 minus 0. So going to be 0 minus 0. This always happens when you take a 3D formula, take something in 2D and put it in 3D, and then you go do a cross product. A bunch of the stuff is 0. That's just how it goes. Okay, lastly here, we're going to do this one. So this is going to be the second derivative. So this will be f double prime minus 0. So this vector is 0, 0, f double prime. It makes sense that that vector points either straight up or straight down. It will point up if it's concave up. It'll point down if it's concave down. So it does tell you a little bit about this. But at that point, we're really fast because the length of the cross product, that's just going to be the magnitude of the second. In this case, it's the absolute value of the second derivative. And then the magnitude of this is going to be, so now on the bottom, so that's why I just got at the top, the magnitude of the cross product. So that simplifies the formula quite a bit. And on the bottom, it's going to be the square root of 1 squared plus the first derivative squared to the third. Okay, so let me do one more zoom out. So we're going to have the square root, because it's the length of the vector, and then we're going to take that and cube it. And under there, it's going to be 1 squared plus f prime squared. So from here on out, if you're doing something in 2D, you don't need the general formula. You can jump straight to the formula in 2D, which is the same formula. It's just saying rather than redo that every time, let's go straight to this. So we're going to take the second derivative, plop it on top. We're going to take the first derivative, put it in here. We're going to square it. And normally we write this as 3 halves. That's it. So that's what the formula becomes when you apply it to a 2D curve. All right, let's get rid of that. And let's apply it now. So it says, if you want the curvature of a 2D curve, you need to plug these things in the right spot. So for the quadratic, the curvature is the second derivative, which is 2. That's already positive, so I don't need to put the absolute value. The positive and negative is really just going to be whether it's concave up or concave down. So you honestly could drop those absolute values and interpret it as if it's negative, it's concave down. if it's positive, it's concave up, and the curvature is this number. But typically we make it positive. Okay, the bottom is 1 plus 2x squared, so it's going to be 4x squared to the 3 halves. That's the curvature of the typical parabola. Now I'm going to pull that up, and we're going to look at it, and then we'll do one more example after that. So here's the standard parabola. I've actually drawn it in 3D, just like we did. And then I computed the curvature formula. And here's the curvature, but I'm going to lay it right on top of it. And it says the curvature is biggest at 0. So I get rid of this. So this says, so it's a totally new function. Now I can already tell that the maximum of this is at 0, simply because the denominator is smallest when this is 0, because everything else there is positive. So I can actually tell that the max curvature, which is kind of an interesting question. And I realize I've made it so you can't see this, but that the max curvature is 2, and it happens at 0. That's what we're seeing. And the curvature is a lot less. So curvature is different than slope, and it's different than concavity. It's a combination of the things. But there you go. You can see that when something's moving along there. You know, if I draw the unit tangent, if I have that ready here, just a moment, I'm going to draw the unit tangent, r of t. Sorry that I didn't have this ready. Plus t1 of t. And I'll make it a little bigger here. So there's the unit tangent. And it's changing the most as you pass through the origin. You can see that. So if I have something moving along, the direction changes a lot right there. In fact, if you fit a circle to the curve, the radius of this circle is actually not 2, it's a half. And I mentioned that, how the radius of curvature is this, 1/2. Radius of curvature. That's a circle that would fit right there. So there's our little study. That's not that interesting. You might have already figured that out. But what about the cube? All right, so we're going to try the cube now. The cube is significantly more challenging. So let's say we have this cube, x cubed, and we want to know where the curvature is greatest. So that's it right there. If you look at the picture, you might suspect that the curvature, it's not at 0. In fact, the function does some funny things. If I'd show you the circles that fit it, and I deviate a little bit, you see that at 0, it's actually really a big circle. But somewhere to the right of 0, it's small, and somewhere to the left of 0, it's small. If you think about if you're watching someone drive on that from above, they're going to be turning the most in these 2 spots here and here. Okay, so let's see if we can find those. So the point of that is, I think it's kind of an interesting question, but how do we do it? All right, so I'm going to get rid of this, and we're going to try again. And you get asked this for any curve. The real point of this is just for you to see that this is just a separate function, a new thing to analyze. So the curvature for the cubic function is going to be 6x on top. I'm sure people have been screaming at the screen like, why can't he do his derivatives? Let's focus on the positive one, the one on the right. And then it's going to be plus 9x to the 4th to the 3 halves. It's much harder to see what the maximum of that is because there's an x in the numerator and denominator. So if I want to maximize this, I want to take the derivative and set it equal to 0. That's a big challenge here. Not that bad, but it does require some work. So let's get after it. So I'm going to take the derivative. So now we're going to jump into calculus 1 territory. I'm going to do a quotient rule, denominator. And I'm going to say a few things about solving here, of why I can attack this and not be scared of it. So denominator times the numerator minus numerator times derivative of the denominator. And this is usually the moment when people are like, I'm ready to give up. It's too complicated. Just stick with us a little bit longer. This happens a lot in math, that the person is just willing to go like a couple more steps in algebra is successful. Okay, I want to know when that is 0. I want to know when the derivative of that previous thing was 0. And when I see this, I go, oh, since I'm just trying to make it equal to 0, it's not so bad to solve. I hope you can see that. A lot of students have this misconception, so I just to say a few general things. If a fraction is equal to 0, that means the numerator is 0. So you can multiply, so you don't need to, you could, I mean, or you can just think about multiplying both sides by the denominator, and that will simplify things a lot. Also, I tell students when I have things equal to 0, I really want to look to factor. And finally, if you can ever simplify, you should do it when you're solving. So anyways, let's just write the numerator out. I'm going to simplify and write the numbers in the way that is pleasing to me. And if we always fight these things, then yes, it becomes much harder. So don't fight it. All right. Did I write here? Okay, good. So now I'm going to write the following. If I was doing this, here's what I would do. I would simplify this. I would say 6 divided by 2 is 3. 3 times 3 is 9. So I'd write minus 9 times 36. So now I've pulled all of these constants out. I had a student tell me they called this the telephone method at their high school. Where you rearrange multiplication. All right, so there's the telephone method. I never heard that before. And now we're going to put the x's together. So I have x to the 4th. There's an x to the 3rd. And then lastly, I have this 1 plus 9x to the 4th. You can see how I kind of sweep across. I don't let myself panic. And in the process, I saw a bunch of things happen like, hey, that looks just like this. Hey, there's some numbers I can pull out. We're really close. Now, most students would move this to the other side, which is perfectly fine, and solve, and you'll be there in a few steps. So it's not as bad as it thinks, as often people think. Just to illustrate something, I'm going to factor more, because what I see is they both have a 6, and they both have a 1 plus 9 x to the 4th. And this is kind of magic the first time you ever see this, it feels like, but it's really not. A lot of times when you have roots and powers, there's some sort of nice factoring that happens. So what can I pull out? I can't actually pull that out to the first because they don't have, this one has it's easier with whole numbers. I find students do better with whole numbers, that if I say factor this, students more easily, let me shrink this down, I keep running into our graph here. Students more easily see that they can factor out an x squared and they're left with an x cubed minus 3. In my experience, that's what I see a lot. But it also works with fractional powers. You just still take the smaller one. Okay, so let's do that. Let's play that game right now. So we're going to do this to the 1/2. When I take that out, what happens? If you take a half out of a 1.5, you're just left with 1 plus, and this is the part that's sort of magical if you've never, to the 1. So there's really no power there anymore. And then I took out the entire 1/2, and I took out 6. So I think if you take 6 out of 36, you're left with, so it's going to be, I think, 54. So minus 54 x to the 4th. And it cleans up so much. So you get 6, 1 plus 9x to the 4th to the 1/2. You get 1. And we're going to have 9x to the 4th minus 54x to the 4th. And again, that 54 is because I pulled the 6 out of this. So let's see if I'm having trouble for a second. Is that 45 minus 45? X to the 4th. We'll find out in just a second. And then if you set this equal to 0, that means either this is 0 or this is 0, and neither one of those things can happen, or this is 0. And then you would find that x to the 4th has to be equal to 1 over 45. Now something feels funny about that, but let's keep going. So we need x to be the 4th root of 1 over 45. Oh, I see. We could write that another way maybe and simplify it. But let's just go there and see. So I'm going to make the value 1 over 45. So I didn't work this out ahead of time, so I apologize if I've made a mistake, but hopefully you have the idea, and we will check this here. So I got 0.386. So let's go there and let's put a few things. Now there are two places, right here and right here, where the curvature is maximum. So that's the curvature function overlaid on there. And let's actually walk to this point and see where the curvature is greatest. Okay, so we're going to walk over there. Oh, I'm on the value. That's why I can't walk over there. So 0.38, so we're going to say 1. So curvature is pretty big. Here's 0.8, here's 0.6, here's 0.54, here's 0.4, here's 0.35, and then it gets bigger. So the smallest at that value, right there when it's smallest, was this 4th root of 1 over 45. If anybody spotted a mistake, let me know, but I wanted to illustrate that piece. In my class, they're having to do a homework question like this, and there's an algebra challenge mixed in there. But I think it is an interesting question of when is the curvature greatest. All right, thanks for listening.